Morning, sir.
Morning, sir.
Just a moment. Okay, let me review last week lecture. Oh yes, announcement ya. Tomorrow you must collect your homework of module 1 at 12 o'clock in the noon. Okay, via Teams. Okay, it's not it is not it should not be late. And then next Friday, this Friday, there will be tutorial class at 9 o'clock. Friday at 9 o'clock. So you can prepare. I will discuss some problems in module 1, especially task E and some of task B. Task B consists of 10 problems as far as I remember. You must read the module 1, read it again, and you can ask the question related to the module at Friday, how to do essentially some problems with effective and efficient way, because usually in exam you have limited hours to work to your problem, so it should be you have to more practice to become easier to solve. I mean, you have to grow your, we call it insight, insight to do some problems, okay? Because in the lecture, I mean, in general, in here in ITB, you have a course, some courses, and then you have they are, I mean, given some problems to you, give some problems to you, and you should do it. Well, you can discuss with your friends, but you have to something like get an idea how to work it, but you have to do it yourself because it it makes you practice. I mean, to think, more practice to think, and then it grows in you, well, some insight or some skill, a skill to think critically. So basically, these problems give it to you. It's you have to do it yourself. You can discuss it with your friends, but with your friend, you discuss how to get the general idea. But you have to do it yourself because it's it's basically train your skill for thinking critically. Okay, train your skill. So it is good to you to do by yourself the problems. Okay. Okay, I will review last week lectures to the last Tuesday lecture. So we have discussed potential energy and electric potential of a charge, a point charge. Okay. So this potential can be viewed, it can be thought as a gradient. So the electric potential can be thought as a gradient of potential, electric potential. We call it V here. Okay, and U is potential, energy potential. This is energy potential. Okay, this V here, but V is electric potential. Okay, so the potential is a scalar unit. It's not a vector. Sorry, a scalar quantity. It's not a vector quantity. So yesterday we have, sorry, last week we have discussed a potential of a point charge and also a continuous charge like sphere. Yeah. So I will discuss I will discuss the potential of a system, so particle system. Okay. So potential electric potential of particle and particle system. So if we have, for example, this is the origin and this is Q, for example. This one is, let's say, the source coordinate, and this is, let's say, this is point P, this is field coordinates, and the difference between them this is vector r minus vector r prime. Okay. So the potential at P in this case is 1 over 4 pi epsilon 0 q over r minus r prime. So if there are, sorry, and charges, it should be summation of this formula, this one particle potential. Yeah? So this basically the system. Let's say total potential at at P here. If there are so many, there are n charges, so it should be 1 over. This should be V1 plus V2 plus Vn. This should be Vi1 and Vi, where Vi means 1 over 4p epsilon 0 qi over r minus ri. Okay, this is for I 1 2 n. Okay, if n is larger, n become larger, or n gets to infinity, so phi will be like this, 1 over 4 pi epsilon 0 integral q. Okay, this is continue approximation nih. Continuous approximation. So you have this integral. Okay, I will give you an example. For discrete charge, this is a discrete charge. This one, I will discuss dipole of two charges. What is a dipole here? Dipole is two charges that have opposite charge, opposite sign to each other. So, for example, if you have, for example, this is X and Y, and you have, you can say, okay, this is, for example, Q, this is minus Q, little q, and the distance between them is D. Okay. So if we consider a point P here, so this should be, this is, let's say, R plus, and this is R minus. Okay. So the potential at P in this case are V1 plus V2, where V1 is, let's say, K Q over R plus, and this is plus minus Q over, sorry, this is K R minus. Okay. And we can write, this is, we can put outside, and this will be 1 over R plus minus R minus. Okay. If we say that R plus is equal to R minus is I'm sorry. Okay. Okay. So, what is the expression, this R minus, with respect to R plus or R and D? Can you say about it? So the factor here, this R minus, let's say this R, this is the magnitude of, this is the magnitude of factor V plus, and V minus, the factor, R minus is equal to R plus factor D. Let's say factor D. The D factor the D vector is di, okay? So basically this one is D vector. Okay, and factor R plus is equal to R is equal to xi plus yg. Oops, sorry. Oh yeah, okay. Is that any question about this? No, okay. Let's continue. So this should be x plus di plus yg. Okay. So the magnitude of R minus, the magnitude of R minus is, let's say, square root x plus d squared plus y squared. Okay, so this should be square root x squared plus y squared plus 2xd. Okay, and this, the magnitude of R plus or R is equal to square root x squared plus y squared. So it should be R squared, oh sorry, this is plus d squared, sorry. R squared plus d squared plus 2xd square root. Okay? So, this could also R, if we put R outside, this is 1 plus d squared R squared plus 2x per rd squared. Okay, if we put this formula to this one, okay, then we can say that this equal to kq over 1 over r minus 1 over, let's say, r 1 over d squared r squared to x over rd. Okay, so we have an approximation here. Approximation. You see from the picture, this d here, the distance between two charges, is very small, very small compared to r. Okay, let's say r. This is in yeah, this r is this one. Okay. So in this case, sorry, 1/3 squared R0. This is goes to 0 plus 2x d over R. Okay, x over R, oh, sorry, x over R, we usually refer to, this is cos theta. What is theta here? Theta is the angle between this one. This is theta. Okay, this is x over R. This R here, this R plus, the magnitude of R plus. Okay. Any question? So this could, let's say, approximate as 1 over 2 okay. It should be, sorry, this is should be R, sorry, not this one. Not this one, but this one. Sorry. So this is squared here. So this should be d over R cos theta, this one. Okay. So potential here, we can write again. VP is F KQ 1 over, let's say, this one. So this would be 1 minus 1 plus 2d over R cos theta minus 1 over 2, 1/2, minus 1/2. Okay? So because this is so small, this d over R, So we can also approximate this function let's say 1 plus minus 1 minus a half 2d over r cos theta. So it should be minus d over r cos theta. Okay. So if we insert this expression to this one, then we get the potential for dipole. This is k q over r squared d cos theta. So the quantity we can introduce p here as a dipole factor is defined as q times d. So this is dipole. And this is the potential. Okay, so you see that this dipole potential depends this dipole potential Vp. Let's say V. Okay, depends on R and theta. So it's no longer spherical symmetric. Yeah. Kp, Kp over R squared cos theta. Any question about this example? Oh yes, I want to make a note about this before I proceed. I want to make a note that you can use this formula. So this formula, you can use this formula. So you have a point of reference, this when r to infinity, at the infinity, this phi r is 0. Yeah? If you use this form of potential, and also this one, so this one you have as an assumption that p plus at infinity is also 0 for this one. Yeah, the boundary condition at the infinity, it should be 0. Any question so far? No question. Okay, let's see some other potential. So maybe if to make it quick, yeah, I will give you an example for continuous. For continuous sample. Let's say a disk, solid disk. So you have a charged disk, charged uniform disk. Okay. So it means that disk is two-dimensional, and uniform means usually sigma constant. Okay, so we have a disk here, solid disk. This is the radius capital R, okay, and this one, let's say, so you can consider the axis, for example. You have this, for example, Z, this is X, and this is Y. Okay? So, what is, for example, this is Q here. So, Q here is sigma times P R squared. Okay? That is the total charge at the disk. What about the infinitesimal charge for the dq, capital Q? So this is sigma over 2 pi r dr. Okay. So basically you have a ring. You have a ring, a thick ring. You have thick, this is a thin ring. You have with it, this is with it, and this is the radius. Yeah, the radius. So this, the cross, if we say draw it again, saying from the top, okay. So this is the radius r, and this is the thick, the width here, dr. Okay. And we consider, for example, a point of the point. This is P here. So the distance, let's say, between them is A, for example. Okay. So DE in this case is K dq over this P. This P is, let's say, square root plus A squared. Okay. Okay. Is there any question about this formulation? Question? No question. So basically this one, this R prime is xi yj, okay? This one is like this, is this, let's say, x squared plus y squared. So what this is, I call this square root. Sorry. This is R prime here, let's say this is okay. Let's say this is prime. Okay, this is prime. Okay, and then this R here, R is AK. Okay, so if you talk about R minus R prime, the magnitude is this one, squared to square root R prime squared plus A squared. Okay? Oh, sorry, this is not E. Any question? No question? Okay, I hope all of you are not sleeping. Any question? Okay. Yes? Hello? Any question? No.
Not
I think
yet,
he
sir.
said not yet.
Not yet. Okay. All of you clear, yeah? Okay. So I just replace this by R prime. Sorry. So this should be K. This should be K 2 pi R prime sigma R prime over R prime squared over A squared, this one. So V here equals to K, sigma is this one. Okay, so it should be 2 pi sigma Q over P R squared integral R prime dr prime over R prime squared so this the below the boundary below is 0 to capital R. Okay, so this you can directly compute this integral. Okay, this is okay, this is 1/2. The integral should be minus half plus 1 R prime squared A squared 0 to R. Okay. So it should be equal to 2kq over capital R squared. Oh, sorry. Yeah. Okay. And this is R squared plus A squared square root. Yeah, 2/2 square root minus A. So this is the potential. So the potential of solid disk, uniform solid disk. Okay. So this is one example. So we have to check whether, so as I said before that if you use this formula, this R to infinity, it should be R goes to 0. Okay. So in this case, let us check whether sorry, just 1 second. Oh, okay. Okay. This R means this R mean in this case is A, okay? This A. If A goes to infinity, then sorry, this electric potential should goes to 0. So it means that this A to infinity, it means that A is much, much greater than capital R. Okay? Then you see that from this function, because A is much, much greater than capital R, it should be dominated by A square root. Okay, and this is A. So A minus A is 0. Okay, so this is this V goes to 0. Any questions? So we have the right formula to use. We have used the right formula. Any question? So what it means? So it means that this disk, if we see from far away, it looks like a point. So a disk, if we look from far away, it looks like a point. Okay. That's the physical interpretation of this formula. This is case number I1. 1I. 2I. What happens if the radius is much, much greater than the distance between the disk and the point P here? So it means that we have a very large disk. It means we have a very large disk. Just 1 second. Yeah. Just 1 second. Sigma. Okay. Okay, we will get this formula. This is Q over 2 pi epsilon 0 R. Okay. Is there any question? Any question?
Sir,
Yes.
sir, I have a question.
Yes.
How do we conclude that R is much greater than A, or A is much greater than R? Is there like a scale, like how many is how many, that we consider that A or R is much greater than yeah.
Sorry, the question is the physical interpretation of the less than R, or R much greater than R, capital R, you mean? The scale.
Yeah, is there like a scale? Like how do we conclude that this is much greater than this?
Oh, okay. That depends on the problem. For example, if A, just 1 second. For example, if let's say A, this is 1 kilometer, and the R, for example, 1 centimeter. So this R over A over R is is 10 to what? Okay, centimeter is 10 to 5 ya artinya. Yeah. This is also the case for this one. For this one, for example, we change the scale. In this case, for example, R is 1 kilometer, A is 1 centimeter. Okay. That's the example. So the so R over A is 10 to the 5. So it means this R greater than A. This is A greater than the capital R. That's for example. That's for example. Anything else?
Okay, thank you, sir.
Yeah. So there is also another example that yeah, I mean, we cannot derive it from this formula. Is this second here, the third example. The third example should be very large let's say, let's say very large rectangular maybe. So very large like rectangular, we have the electric field is proportional, is equal to sigma 1 over 2 epsilon 0. Okay, so basically this this electric field is derived from the Gauss equation. So there is a sigma here, which is constant, and we have this cylindrical surface, and for this one. So this is A, this is A here. So from Gauss equation, we get this formula. This one from Gauss formula, Gauss law. Okay, so what about the potential of this rectangular, this very large rectangular? The potential is, if we have, let's say I draw it again, this is rectangular, very large rectangular. Okay, and we have a point here, A. A is very small. Very small. Very small. Compared to what? Yes, very small, big, bigger. Much smaller, smaller. Then let's say the length of this rectangular. Okay, this formula only valid for this A is smaller than the length of the rectangular. So the potential in this case, B, is equal to integral 0 to C, for example, sorry, to A, sorry, this to A here, E dz. Okay, this is integral 0 to A. This is Muhammad Arasha is late or he has a problem with connection. Can you ask Senin? Hello, Senin?
He said that he was, yes, hello, sir.
Yes, this Muhammad Arasha is he late or?
No, he said he was disconnected.
Disconnected, okay.
He got disconnected, yes.
Okay, thank you. this is sigma, sorry, this is sigma over 2 epsilon 0 dV. Okay, so this will be sigma z over 2 epsilon 0. So this v here depends on the z. Z over 2 epsilon 0. Any question at this level so far? Any question? Okay. You can, for example, what about the solid ball? Solid, sorry, so not solid ball, solid sphere. Solid sphere. Again, this density is constant. Charge density. Homework, additional homework. So you will be collected this homework next week, yeah, on Monday. Please collect it on Teams. Okay.
Sure.
Oh yeah, solid sphere with radius capital R. Sorry. Homework, yeah, homework. Okay, I will stop the share the micro from Microsoft Whiteboard. Okay, I will share the book. Let's see. Anyone see it? Anyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Can you
sir.
read? Can
We
you
can see
read? Can you read? What's the title of the book? The title of the section?
potential due to continuous charge distribution.
Okay, okay. So this book is from Heide Resnick Walker. I forgot the edition. I think you can get it in the internet. So this is the potential what we have discussed today. This R here, okay, this dq here, it could be positive or negative, depends on the charge, of course. Yes. Oh, sorry. Before that. Okay, we have discussed this electric dipole. Yeah, if you read this one, well, basically the same as we have this one. We get this potential. Okay, this equation, and then okay, this is the potential P here. P is the dipole, electric dipole moment, we call it. Electric dipole moment, P. Okay. So in this case, I just make a remark here. If this D here is very small, is smaller, much smaller than this R plus or R minus or R here. R is in the middle of this distance, in the middle of distance, this R to P. So if D is much smaller than R, this R plus and minus is parallel. So in this picture, it's not parallel. It's R plus and R minus. But in this second or this 2410b figures, yeah, it shows that this R plus and R minus is parallel to each other. So in order to have this case, we have to set this D here is very much smaller than this R. Okay, so we will get this equation 2430. So this is the dipole system. Can you give an example of a natural dipole system, for example? Natural dipole system, also dipole system in the nature. Can you mention it? Hello. Arkan Rashad Usman. Hello?
Yes, sir.
Yeah. Can you mention about the dipole system in the nature?
So a dipole, it's comprised of two opposite charges.
Sorry?
What's the exact question, sir?
Example, can you mention the example in the nature for dipole system? Example of dipole system. It means that it consists of positive charge and negative charge. They have exactly the same charge, but the opposite sign.
Magnet?
Ahmad Rishad Tohir. Yeah.
I still quite don't understand, sir.
Sorry? Hello?
Still quite don't understand, sir.
Can you
Can you hear me,
mention,
sir?
can you give the example of dipole system in the nature?
In nature.
In the universe.
I don't quite have the answer, sir.
Reno. Hello, Reno.
Yes, sir.
Yeah, can you mention the example of dipole system in the nature?
A water molecule.
Yeah, molecule. Which molecule? Molecule is so many.
Water, sir. H2O, right?
Yeah, exactly. Like water. Is there any the simplest example in the nature of the dipole system? Is simpler
The
than
Earth pole.
H2O.
The Earth pole, sir.
Earth pole is a magnetic dipole. It's not electric pole. It's not electric
How
dipole.
about the ground and the clouds, sir? Like the events of lightning, sir. Is it a dipole as well?
Yeah, it can. but the simplest example of electric dipole in the nature. H2O, water, okay, but there is the simplest thing, the simplest electric dipole. Nicholas Aryandra.
Tes, hello.
Yeah.
I don't know. I had the same answer as Reno, sir, like water molecule.
Okay. Alvino, Theondra. Can you mention
Yes, sir.
the example, the simplest example of electric dipole in the nature?
I also had the same answer, sir, like water molecules.
Selin.
Yes, sir.
Yeah.
Electric charges.
Sorry?
Electric charges.
No, it's monopole. I mean dipole. Rafa.
Yes, sir. I'm still thinking as well.
Sorry?
I'm still trying to find another answer besides water molecule, sir.
Okay, Sultan.
Yes, sir.
Yeah.
Still thinking, sir. How about battery, sir? Is it?
Not battery.
It
The
has
simplest.
two opposite pole.
The simplest
Positive
thing.
and
The simplest electric dipole in the nature. Can you mention?
I don't know,
It's
sir.
the only one.
Sorry.
I think it's the only one. No, it's not the only. Yeah, it's not the only one. Sorry, but okay. Okay. At your level, the simplest. At your level, okay. At your level, as far as you know, at your level, the simplest electric dipole is hydrogen atom. Okay, hydrogen.
Also, is it like proton and electrons, sir?
Yeah, exactly. In hydrogen atom contains only two particles, protons. The charge, its charge is positive, and then electron, and its charge is negative. Okay, that's the simplest electric dipole at your level. At advanced level, there are so many, especially in elementary particle, but I do not want to mention it. But at your level, it is the simplest thing, the simplest electric dipole is hydrogen atom. Okay? That's the case. Okay, let's back to this continuous charge distribution. So this is the line charge here. This dq here equal to lambda dx. Okay, lambda is the charge density of rod. Yeah, it's charge density per length. Okay. Well, basically, mostly lambda considered to be constant, so the rod is uniform. Okay. So this is the 2434 is the infinitesimal potential of the rod. Yeah. So basically this R here, R is this one here, okay? This one, x squared, square root of x squared plus d squared, this one. Okay, and then we get this one. Then the integral should be like this, okay? So this 2435 is the potential of the line element, the rod, the potential of the rod, charge rod, uniform charge rod, okay? So if d goes to infinity, it means that d here is much bigger than L is the length of the rod. Then you can show that this 2435 here, this formula, this V here, goes to 0. Okay, you can see directly. Okay, let's say for the rod, rod, yeah, uniform charge rod with length, let's say L. Okay, we have seen that this is lambda over 4 pi epsilon 0 log L plus L squared plus B squared square root over D. Okay. If D goes to infinity, or D is much bigger than L itself, okay, this log here, this will be the square root over D, which is goes to 0. So this V is goes to 0. Okay. So it means that, as we discussed before, just now, yeah, the rod, we see the rod we close, we see the rod, we see closely, it is the rod with length capital L, and if we see from far away from the rod, and the rod looks like a point particle. Okay, that's what it means. Okay, that's okay. Let us stop here. Okay, we continue, and we have discussed this charged disk, uniformly charged disk. So we have this formula, okay, 2437. We have discussed it. Okay, and then how to calculate the field from the potential, for example. So this, so as we have also discussed that the potential is the gradient of the scalar potential, electric field can be viewed as the gradient, minus gradient of the scalar potential. And we can write like this, okay? Okay, this, for example, we have this potential here. Okay, this potential. Okay, this potential here. And then starting with this expression, derive an expression for the electric field at any point. So you see that because this potential only depend on Z, so it means that we can express the electric field in terms of the gradient minus gradient of the potential. And because this only depend on Z, so we have the derivative of total derivative of d over dz, and then we get this expression, this final expression. You see that if the z goes to infinity, or the z much larger than the radius, so we have that what is it? This become very large, or it can equivalently, it's the same as the very large rectangular. So we have the constant electric field, which is equals to sigma over 2 epsilon 0. Okay. Any question? Any question? Any question? No? Okay. So again, we will consider about electric potential energy. For example, for a point particle. Okay, let's say we have two charges, 2 point charges is Q1 and Q2, both positive. And then the potential, in this case, you see that here, Q1 can be viewed as the source charge. So this Q2 is the test charge, and the distance between them is, let's say, R, okay? And the potential of the Q1 given by this one. This one, okay? Then the electric potential energy of a system, in this case, these two charges is equal to this one. K times Q1 times Q2 over R. Okay. So because this is a scalar quantity, this electric energy potential, so it means if we have more than 2, for example, 3, 4, 5, the same as the electric potential, we just add it. Yeah, we just add. I will give you an example. For example, if we have 3 charges like this, it forms a triangle with the same side. Yeah, this D here, D and D. So what is the total potential energy U in this system? So basically you have 3, yeah? Q1 and Q2, the distance between is D, Q1 and Q3, the distance between is D, and then Q2 times QD, and the distance between them is D also, okay? This Q1 is, for example, plus Q, Q2 is minus 4Q, and this Q3 is plus Q plus 2Q, okay? So 1, 2, for example, 1, 2, sorry. Okay, I have to make it slowly. Okay, so U1 here, yeah, U1 like U1 2, so like this, yeah, the distance between ND, and also 1 3 and 2 3. Okay, we have this one and this one, and then the total potential energy U here is the sum of all of them, because we have 3 charges, so we add all of them. Okay, U12 plus U13 plus U23. Okay, so we get it totally is this one, this minus 10 q squared over 4 pi epsilon 0 d. Okay, let's say if the q, we take this 150 nano, yeah, nano charge, nano coulomb, yeah, nano coulomb. So nano means 10 to the minus 9. Okay, and we get this potential energy is minus 17 millijoule. Is there any question?
No, sir.
Okay. So the minus, the sign minus here mean, you see it from the statement, that negative work should have to be done to assemble the structure. The external agents, what have to do is, have to do 17 millijoule of work to the assemble of the structure completely. So it means that we need 17 millijoule to destroy the structure. Okay. Is there anything else? Okay, just some remark here, some statement, small statement. So in electrostatic problem, yeah, because the electric potential can be expressed in terms of the scalar potential, and also the force of electrostatic force, this F equals to QE, for example, it's a conservative force. So it means that if you have the case, for example, like this particle alpha repelled by, for example, gold nucleus. Okay, in this case, because the alpha particle is a charged particle and also the nucleus, so in this system, it admits the conservation of mechanical energy. Okay, in this case. So it means that the total mechanical energy before equals to total of mechanical energy after. Before collision and after collision, for example. That's some remarks. Okay, any questions? If not, I will summarize our lecture here today in Bahasa Indonesia. Any question?
Belum ada, Pak.
Okay, okay. Oke, jadi saya simpulkan untuk kuliah kita hari ini ya. Sebentar. Ini juga agak terlambat. Oke, jadi kita udah bahas tentang contoh-contoh penggunaan potensial ya. Jadi potensial itu adalah kuantitas skalar, besaran skalar ya. Jadi kalau potensial itu misalkan seperti ini. Jadi seperti ini misalkan ya. Jadi ada O itu adalah titik asal, Q itu adalah di sini bentuknya, dan ini adalah titik P di sini. Nah, jadi antara O dengan P itu kita nyebutnya ada sebuah koordinat yang namanya koordinat medan yang R ini, R vektor. Kemudian ada lagi yang potensial koordinat sumber ya yang saya gariskan. Oke, jadi rumusnya itu adalah VP itu adalah 1/4pi epsilon 0 Q per R kurangi R vektor R kurangi vektor R prime ya, besarnya. Nah, jadi kalau dia itu ada N buah muatan, itu tinggal Anda jumlahkan saja yang saya simbolkan seperti di sini. Yang saya simbolkan seperti di sini. Oke, jadi ketika N-nya itu sangat besar, ya, artinya kita bisa menggunakan aproksimasi benda kontinu, ya. Sehingga nanti ini bisa kita nyatakan seperti ini bentuk integralnya. Ya, jadi dengan persyaratan bahwa ketika kita menggunakan ini, syarat batas yang harus dipenuhi itu adalah ketika ditahingannya itu menuju 0. Nah, ini saya kasih contoh misalkan untuk dua buah muatan yang kita sebut namanya dipol. Oke, potensialnya seperti ini. Ya, ini tentunya dengan aproksimasi gitu ya. Nah, potensialnya seperti ini. Ya, tentunya kalau R-nya menunjuk tak berhingga, ini udah pasti 0. Oke, jadi dipenuhi. Kemudian yang untuk benda kontinu, misalkan muatan uniform ya, disk cakram bermuatan ya, dan dia uniform, jadi sigmanya itu konstan. Ya, kita udah dapatkan rumusnya seperti ini. Kita dapatkan bentuk integralnya. Ya, jadi bentuknya seperti ini. Kemudian kita harus cek apakah yang kita lakukan ini benar gitu ya. Jadi Anda bisa cek kalau A-nya itu menuju tak berhingga, ya, artinya A itu sangat-sangat jauh lebih besar dibandingkan radiusnya atau R besar. Maka rumus seperti ini akan R kuadrat plus A kuadrat itu akan menjadi A kuadrat saja karena A kuadratnya mendominasi. Oke, kalau kita akarkan dia menjadi A, jadi A dikurang A jadi 0. Jadi dia memenuhi ya bahwa ini menuju 0. Artinya apa? Bahwa kalau kita lihat dari dekat, ya, cakram itu, ya itu bentuknya cakram. Tapi kalau kita lihat dari jauh, yang sangat-sangat jauh, jaraknya itu terlihat seperti titik, gitu ya. Nah, jadi contohnya misalkan teman Anda tadi tanya, berapa sih yang kita katakan itu sangat besar ataupun sangat kecil, ya itu bergantung. Ya, biasanya tuh kalau ada perbandingan di atas 10⁻³ itu dia udah dianggap besar. Ya. Sudah dianggap besar. Jadi istilahnya untuk mempermudah desimalnya saja. Gitu ya. Jadi saya kasih contoh. Kemudian yang kasus kedua ketika R-nya itu sangat jauh lebih besar. Jadi artinya disk itu sangat besar lah gitu ya. Ininya. Jadi itu didapatkan bentuk potensialnya cuma seperti ini aja. Ya. Jadi kalau R-nya sangat besar ya bentuknya seperti ini. Kemudian ada lagi sebenarnya yang bentuk rektangular, jadi bentuk persegi itu ketika sisi-sisinya itu juga sangat besar gitu. Jadi artinya sangat lebar ininya. Nah, dari hukum Gauss itu didapatkan bahwa E di sini tuh konstan, yaitu sama dengan sigma per 2 epsilon 0. Oke. Nah, kalau misalkan kita ambil misalkan apa? Titik itunya berjarak tidak jauh dari tidak jauh dari perseginya gitu ya, atau katakanlah dia lebih kecil dibanding dengan sisi-sisi dari persegi gitu ya, atau bentuk sangkarnya, itu kita dapatkan ini ya E-nya, dan V-nya itu dari 0 sampai A ya batasnya. Jadi 0 itu kita ambil di dekat dekat istilahnya pada perseginya gitu ya. Nah, jadi didapatkan rumusnya seperti ini gitu ya. Ini potensialnya. Nah, potensial ini sangat bergantung pada Z. Jadi karena Z-nya itu jauh lebih kecil dibanding dengan sisi-sisi dari perseginya gitu. Kemudian ini contohnya lagi, Anda buat PR ya untuk bola bermuatan padat ya, bola padat bermuatan solid sphere, radiusnya R besar, rho-nya diambil konstan, potensialnya gimana? Kemudian ini kita bahas juga terkait dengan batang ya, batang juga itu potensialnya seperti ini ya. Batang bermuatan dengan panjang L, ini juga sama, kalau A-nya itu sangat-sangat besar dibandingkan panjangnya, maka rumus ini juga akan menjadi V-nya itu akan menjadi 0 ya. Jadi artinya bahwa batang itu kita lihat dari jauh itu terlihat seperti partikel titik. Sama juga seperti galaksi kita juga, jangankan cuma batang ini aja. Galaksi kita tuh kalau dibanding dengan ukuran alam semesta, itu dianggap seperti partikel titik. Nah, Anda kebayang kan? Kalau galaksi aja yang sangat besar, yang berapa ratus miliar kali bumi gitu ya, itu dianggap partikel titik dibanding dengan ukuran alam semesta. Nah, sekarang kan Anda kebayang kalau bumi itu dianggap apa gitu ya. Seperti itu. Jadi kurang lebih skala seperti itulah. Ya, sampai sini dulu ada pertanyaan nggak? Sebelum saya share di yang holiday week-nya.
Pak.
Ya.
PR yang solid sphere itu buat
minggu
kapan?
Depan Anda kumpulkan hari Senin.
Oke Pak, terima kasih.
Nanti akan di Teams akan saya buat. Jadi ada PR modul 1, ada PR yang kecil-kecil yang kayak tadi. Ya kecil sih itu, kalau ada itu lumayan gitu.
Oke Pak.
Jadi dibedakan.
Maaf Pak, saya mau bertanya Pak.
Iya.
Untuk PR modul tetap besok jam 12 kan Pak?
Iya besok.
Oke.
Jadi PR itu nanti ada PR modul, jelas biasanya tetap tiap minggu ada. Kalau yang PR tadi mah biasanya di luar dari waktu modul biasanya. Itu untuk latihan Anda aja. Oke?
Oke, terima kasih Pak.
Ya, sama-sama. Oke, jadi yang ini tadi contoh-contohnya ya. Ini cuma sekedar ini aja. Jadi ini kita menghitung tadi contohnya ya. Itu adalah bagaimana kalau kita tahu potensial, menghitung potensial medan listriknya gitu ya. Itu seperti ini. Jadi medan listrik itu dianggap sebagai gradien dari potensial. Ini saya ambil contoh, nih kita dapat yang tadi kan tentang cakram bermuatan ya, uniform ya. Rumusnya seperti ini, gitu. Ya, nanti tinggalkan aja karena di sini tuh bergantung pada Z saja, maka juga gradiennya hanya bergantung pada Z saja gitu ya. Jadi ini nanti diturunkan nanti apa namanya medan listrik pada sumbu Z itu kurang lebih komponen vektornya itu seperti ini. Sigma per 2 epsilon 0. Oke. Kemudian ini juga kita bahas tentang apa namanya energi potensial ya, yang disebut U gitu ya. Jadi ada potensial sumber Q1 ya, Q1 sebagai muatan sumber, Q2 itu sebagai tes partikel atau muatan uji. Atau juga sebaliknya, Q2 bisa kita taruh sebagai muatan sumber, Q1 uji sama aja. Tapi kalau Anda lihat di sini potensialnya, potensial dari dua sistem tersebut, Q1 dengan Q2 yang dipisahkan oleh jaraknya R, itu bentuknya sama ya. Bentuknya di 2443 ini. Ini saya ambil contoh untuk yang kasus 3 dimensi, 3 partikel, membentuk segitiga sama sisi. Ya. Jadi seperti ini. Nah, Anda lihat di sini juga energi potensial itu merupakan jumlahan dari U12, yaitu antara interaksi antara Q1 dengan Q2, U13 itu Q1 dengan Q3, Q2 dengan Q3. Jadi tinggal ditotalkan, didapatkan, karena semua sisinya sama, kecuali muatannya, itu dapat adalah minus 10 Q kuadrat per 4pi epsilon 0 D. Karena ini jarak-jaraknya masing-masing D. Oke, itu aja dari saya ya. Kalau nggak ada pertanyaan, saya